In this section, we're going to talk about an introduction to what we call a derivative. So first of all, let's go back to our more basic math classes and talk about a tangent line. So remember, if you have any curve, y equals f of x, you can look at a specific point and you can find the slope at that point. And if you were to draw in a tangent line, the tangent line would also have that same slope. And the idea is, if you zoom in closer and closer and closer and closer and closer and closer until you look at just that tiny little point, your function and your tangent line would be almost indistinguishable, or until that tangent line is truly the slope of the curve at that one point. And that's how you define the slope of a curve, is, well, what would the slope of the tangent line be at that one point? And really, to find the slope of a curve, because it's not a line, you have to zoom in really, really far until it just looks like a straight line. And sorry, we don't have really good resolution here, but you can kind of see the same idea of I've been zooming in further and further and further. So now I've zoomed in further and further and further, and you can see that this curve, if you zoom in far enough, that curve from right here, that curve is almost indistinguishable from the tangent line. So that's how you find the slope of a curve. Okay, so now we introduce something called a derivative in slope. So what we want to be able to do is we want to say, okay, if we have any function f of x, let's figure out how we can find the slope at any given point. So the slope at any given point, if we can find that formula, we would call it f prime of x. That's called our derivative. So it would be the derivative of x. F of x. And we put that little notch right there, that prime, to say that it is a derivative. So in other words, again, if you have your function f of x and you find any point, you find the slope at that point, that slope would be the derivative, f prime of x. So in this section, we just give you a few basic formulas. We're actually going to learn a lot more about taking derivatives in a few sections, but for now, just a few simple formulas. First of all, if you have a straight line, the equation of the line is y equals mx plus b. And you know that if you have a line, the slope is m. So if we have the function f of x equals mx plus b, then the slope at any point would be m. And we can call that f prime of x, because that is our derivative. Our derivative is the formula that gives us our slope. If you have a horizontal line, so if you have f of x equals b, so you could have examples like f of x equals 2, or f of x equals 3, etc., just any straight line, then the derivative of this will always be 0, because for a straight line, your slope is 0. So if f of x equals 2, then f prime of x would be 0. If f of x equals 3, then f prime of x would be 0, because our slope is always 0 for a horizontal line. Okay, then we have one basic power rule. Okay? And this will let you do the problems in this section, and then we learn how to get more complicated. So if f of x is just x to the power of r, so r is just any number, so x to the power of 2, x to the power of 3, 5, 6, 7. You can even do negative exponents, like x to the negative 2, x to the negative 3, etc. Then the derivative, what you do is you take this power and you bring it down, and it multiplies the x. And then you drop the power by 1, so you do r minus 1. So let's see what that looks like. So find f prime of x for f of x equals x squared. So f prime of x, okay, you take your exponent or your power and you bring it down, and it multiplies the x, and then you drop your power by 1. So 2 minus 1 is 1. Or we could simplify this to 2x. In our next example, f of x equals x cubed. So you bring down that 3, you bring the power down, and then you drop the power by 1, or subtract 1 from the power. So 3 minus 1 is 2. So we get 3x squared. Let's try a more complicated one. What if f of x equals 1 over the 4th root of x? So sometimes you have to rewrite f of x to make sense of this. So first of all, if it's in the denominator in the bottom of a fraction, that means x had a negative power. And a 4th root like this is the power of 1 over 4, if you remember your basic math classes. So really now we have x to the power of negative 1 over 4. So f prime of x, you bring that entire power down, so it'll be negative 1/4 times x, and then you take that power and subtract 1. So this is negative 1/4 x to the power of negative 5 over 4. And you could leave it like that, or you could write negative 1 over 4 x to the power of 5 over 4. So that's how you can use the basic power rule to find your derivative or the slope at any point. Now let's look at some more application type things. Let's look at finding the slope at a single point. So if we want to find the slope of a graph at the point x equals a, we find the derivative f prime of x, and then plug in our specific x value of a. So we write this as f prime of a. So f prime of a tells us the slope of the graph f of x at the point x equals a. You could also think of it as it's going to be the slope of the tangent line at the point x equals a. So then we can do an example like number 3, where we want to find the equation of the tangent line to the graph f of x equals 1 over x squared at x equals 2. Okay, so we want to find the equation of a tangent line, but to do a tangent line we need to know the slope. To know the slope, we find the derivative. So let's find the derivative of f prime of x. Now f of x is 1 over x squared. I'm going to rewrite that as x to the power of negative 2. So now I can use my basic power rule. So that negative 2 comes down and we multiply x. And then you take this x and you drop the power by 1. So you do negative 2 minus 1. And the negative 2 minus 1 gives us to negative 3. Okay, or this is negative 2 over x cubed. So now let's find, that's our slope at any point. Now let's find it at the specific point of x equals 2. So at x equals 2, we're going to have negative 2 over 2 cubed, which is, let's see, negative 1/4. So the slope at x equals 2 is negative 1/4. So now our tangent line. To do a tangent line, you need a few things. You need to know the slope, and you also need to know the function value. Okay, so we know our slope. Okay, well let's first do this. If you want the equation of a line, we do y minus y1 equals m times x minus x1. So in our case, our slope is that negative 1/4. But we need to know what's y1 and x1. What is our actual point? So if x equals 2, then y would be equal to what? Y is, well, let's put our little ones here. So if x1 equals 2, then y1 is going to be f of x1 or f of 2. That means plug 2 into your original equation, not the derivative, but the original equation. So that's going to be 1 over 2 squared, our original equation. Okay, gives us 1/4. So it's unfortunate that my y value and my slope are very similar. That could be slightly confusing for us here. But now let's plug it into the equation of our line. So y minus our y value is 1/4 equals our slope of negative 1/4 times x minus our x value, which is 2. And that is the equation of our tangent line. Unless we're told otherwise, we don't have to find slope-intercept form, or we don't have to simplify. We can just leave it like this. If you look on your textbook, the bottom of page 76, there's a very official formula for the equation of the tangent line. I don't like memorizing new formulas if I don't need to, because you can find the equation of the tangent line using your old point slope form. So you can memorize that new equation on the bottom of page 76, or you can just keep using the form you memorized years ago. Okay. Now, we kind of showed you some basic rules, but we just kind of pull them out of thin air, and you don't know why we were doing them the way we did. Okay. So to do that, we go back and we do a little bit of theory. Okay. If I want to find the point, the slope right at this point, we have to go back to say, okay, how did we find slope in previous math classes? We only know how to find the slope between 2 points. So what you do is you find what's called the secant line, which is 2 points. Okay? And the slope of that secant line is not going to match the point right there exactly, is it? But what if I did put my secant line just a little bit shorter and got a little bit closer. And I got a little bit closer and a little bit closer and a little bit closer. So we want to move the 2 points closer and closer, until eventually, if I can move them so close that they're essentially the same point, I could find the slope at that exact point. Okay, so you start off with 2 points that are far away, you move closer and closer and closer and closer and closer until you get to just 1 point, and that would be the slope at that 1 point. So the way we do this theoretically is this is my actual value, f of x. That's what I want to find the slope of. So you take another point that's further up. To be general, we'll just call this f of x plus h. So what this means is here's my x value, and you just go over a little bit. We're not going to say x plus 1 or x plus 2 because we want it to be general, so we do the number h as a constant, any constant. It could be 1, 2, 3, etc. So you go over just a little bit, and so this y value be f of x plus h. And we want to find the slope between these 2 points. So what is the slope between these 2 points? So slope is equal to, you subtract your 2 y values. So what are my 2 y values? The difference between here, these y values, would be f of x plus h minus f of x. So subtract your 2 y values. We subtract our y values. Then you subtract your 2 x values to see how far you went over. So let's see, we did this top point first, so let's do the x plus h first. And then let's do the x. Okay, so we subtracted our y's, we subtracted our x's. Okay, and we can simplify this to f of x plus h minus f of x all over, notice those x's cancel, so we just have h. So that's the slope for any arbitrary point. So if we have the point we want and we go up to any other point, we can find the slope in between using this kind of complicated looking formula. And then the idea is we can go through and we can say, what if these points get closer and closer together? So these points get closer and closer. We want to get closer and closer to our actual point, because then the slope will actually match up to the slope at that point. So if we want to get closer and closer to our actual point of interest, we're going to let h get smaller and smaller. Now this idea of getting closer and closer is something called a limit. And we haven't actually talked about limits yet. We do it in the next section. So it's kind of an interesting order to go about it, but that's the way our textbook does it. So we want to get closer and closer by letting h get smaller and smaller. So let's look at this theoretically. So we can find the slope of the secant line, so 2 points, by f of x plus h minus f of x over h. This is called the difference quotient. What you'll do is you'll find this quotient, and then you'll simplify as much as possible. And then we'll let h approach 0. So that means h gets really, really small. Okay, and if you do that, then the slope of your secant line will get closer and closer to your slope at that specific point, or the derivative. So we can use this to actually find derivatives. It's a very difficult way to find derivatives. We only do it once or twice, and then after that we learn more formulas that let us do it without all the actual work and simplification. But let's try it once. So use the difference quotient to find the derivative of f of x equals x squared. So we need to find f of x plus h minus f of x all over h. Okay, so first f of x plus h. What you're going to do is go to f of x and put in an x plus h wherever you see x. So instead of x squared, we'll have x plus h squared minus f of x, which is just x squared, all over h. Now let's simplify. So x plus h squared, you actually have to factor that out. So do x plus h times x plus h, which is x squared plus xh plus xh plus h squared. Okay, so let's simplify that a little bit. X squared plus 2xh plus h squared minus our x squared over h. So again, you always have to simplify as much as you possibly can. So let's see, this x squared and that x squared, notice that those will cancel. So we don't have to worry about that anymore. So we have 2xh plus h squared over h. Now if you're doing this correctly, you should always be able to kind of factor out an h or get rid of an h. So you could factor out an h from the top. So you have h times 2x plus h over h. Notice now we can cancel those h's and we get 2x plus h. Okay. So this is our simplified difference quotient. I still have no idea what that h is or what it's doing for me. I kind of want to get down to just x's. But remember, we want h to get small. So as h gets really, really small, okay, what's going to happen here? Our 2x plus h gets really close to what? If h gets really close to 0, what's 2x plus 0? It would just be 2x. Or h starts off as 1, so we get like 2x plus 1. Then if it gets down to a half, 2x plus 1 half, 2x plus 1 fourth, 2x plus 1 over a million, 2x plus 1 over a billion. So basically h gets so small that it just becomes like 0, and we'll just be left with 2x. So finally, officially, the derivative f prime of x is 2x. And again, in our next section, we'll talk about how you would actually find those limits, or as h gets really small, how you'd find that more officially.